Hi, everyone hear me? Yeah, well, thanks for everyone for taking the time to come to the talk. We're going to be talking about some of the more advanced language features of Scala. So maybe not advanced, but ones that haven't made it into mainstream languages like, say, C# or Java. The theme of the talk is going to be trying to rely on the language or the compiler or the standard library rather than using other proprietary frameworks that perhaps use things like runtime reflection under the covers. So my name is Christopher Batey. I work for Lightbend, which is the company, one of the main backers of the Scala programming language and one of the main contributors to the Scala compiler. But I actually prepared this talk before joining, so that is a complete coincidence. And most of the examples that I come from building things like web apps and Spark data pipelines and things rather than anything too esoteric. However, since joining Lightbend, I've worked on this library and framework. It's Akka. It is a concurrency. It's an actor-based concurrency model as well as a distributed systems toolkit. And that's definitely fed more content into this talk because Akka itself is written entirely in Scala, so that's a language which I work in 95% of the time. However, it has a fully fledged Java API. So every time I come to add a feature to Akka or I'm reviewing a pull request for a feature inside Akka, whoever's done it needs to provide both a Scala and a Java API, which I think is quite interesting because I constantly get to see the differences between the two programming languages, the different feature sets, and what are the different idiomatic ways to use the two languages. So the agenda for the talk is going to be, I'm going to talk a little bit about programming language terminology to make sure I don't use any terms we're not familiar with for the rest of it. I'm then going to go into the main motivation for the talk, the one that the whole talk was going to be about originally, which is to use function composition, partial application, and currying instead of a traditional layered and hexagonal or ports and adapter style architecture. I'm then going to go into something which, if you'd asked me 5-10 years ago working in Java, would this be a useful feature for the mainstream, I'd have said no. But the way programming is going and the fact that more and more of our programs are going to be asynchronous and the fact that we're representing that asynchrony in the type system with things like completable futures in Java and futures in Scala, I think the ability to abstract over higher kind of types is something which will hopefully get into the mainstream. If you don't know what that is, that's what the talk's about, so I will introduce that and so why I think it's going to be useful. I'm going to end up on definitely the most controversial part, I think, of the Scala programming language and probably the talk, is to talk about implicits. So implicits are a feature of Scala which, if you've dabbled slightly or you've got a colleague at work who hates Scala, I would bet they would say it's because of implicits, and we're not going to use Scala because of that. But there isn't one implicit feature, there are many. I'll go through a couple today, and if you want to discuss some of the other ones and their use cases and their pros and cons, then just grab me after. As the talk goes along, we'll be going through more and more advanced features. So if at the start you're like, I know what that is, come on, that is the basics. Don't worry, it's going to get more advanced, but I didn't want to leave anyone behind. So programming languages. Who here programs in Scala on a day-to-day basis? Okay, you might get bored, but no. What languages are you programming in? Java? Yep, C#, a few. Kotlin? Well, fewer than expected. Right, so I think programming languages are fun. I think learning new programming languages is fun, and I think as you learn them, you're able to pick up programming languages more quickly, especially if the programming languages are in the same paradigm. And one of the biggest obstacles to programming in Scala is the fact that it is a new paradigm. You know, you can do pure functional programming in Scala, and 10% or 5% of the ecosystem might do that, and then the skill set from Haskell might be useful. You can also write virtual Java with removing some of the warts. But I don't think that is the essence of what's fun about programming in Scala. I think it's better to treat it as the language it was designed to be, and that's a hybrid between functional and object orientation. And some of the examples I'm going to show you today are using things that you would normally find in a functional programming language, for instance, function composition, currying, partial application, but we're still going to use it even if we're structuring our objects or our program in terms of classes and objects. So we're going to start off with something that I think is the most fundamental part of a programming language, and it's both distinguishing and learning the different semantics and syntax of a programming language. So the semantics of a programming language are its behavior, what the stuff you write actually means. So is it expression-based or is it statement-based? Is immutability the default? How do you do concurrency and parallelism? These things are really important, but they're also really easy to learn. If you don't know Scala, and I don't know Kotlin, and we went for a coffee together, we could teach each other the semantics of a programming language very quickly. You could tell me whether the control flow structures are expressions or whether they're statements, and I would leave that conversation knowing the language very well. However, syntax, which is what we type, do we have curly braces, or is it Lisp-based? Do we need semicolons? That's the kind of thing which takes a long time to learn. You have to type. Unless you're a genius and you're able to memorize this stuff very quickly, it takes a long time to learn and become very fluent in the syntax of a programming language. And maybe that's not important, but while you're still thinking about the syntax of a programming language, it's very hard to actually concentrate on the core semantics and the actual business functionality you're trying to develop. And I certainly have this problem, and I think a lot of people have this problem, that when we get into unfamiliar syntax, when we're learning a new programming language or we're seeing a different paradigm, then we often confuse this unfamiliar syntax with complexity. And we forget that we've been programming in a C-style language for 10 years, and we're so used to that. So there's one thing to take in mind. I'm going to show you quite a lot of new syntax throughout this talk if you've not done a lot of Scala. And what I want you to do is not go, "Ugh, that looks horrible." Let's just try and take away the semantics and the behavior of the programming language. So what is the most important thing about a new programming language when you're going to learn it? Well, I would say whether it's expression-based or statement-based. So here's a question for the audience. This is Java, not Scala. What does this evaluate to in Java? Say the value of x is 12. Any guesses? No? It doesn't compile. And this is the only bit of Java or Scala in this presentation that doesn't compile. The way I create my slides it scrapes code from an actual project which you can take away and pulls it into HTML slides. And the reason this doesn't compile in Java is it's a statement-based language, which means your control flow structures like ifs and whiles, they don't evaluate to a value. You have to do something side-effecting inside the blocks. Otherwise, you may not have written it. So here's another bit of Java which does compile. And if things are statement-based, then what it encourages is mutability, because one of the fundamental side effects of programming is mutating state. Now, the only, I think, exception in the Java programming language would be the ternary operator, which does evaluate to something. So you can assign the result of a ternary operator directly to a variable. What about this? Does this compile? Well, I've already told you, really, because I said there's only one bit of code that doesn't compile. But this compiles in Java. But if you were to use the should act variable any point in the rest of your code, it would stop compiling, because it would say it'd be uninitialized. And that's one of the interesting side effects of a program being statement-based, of a programming language being statement-based. So about this is Scala. So what does this evaluate to in Scala? Let's say the value of x is 12. Well, I'd hope it would evaluate to true. And the fundamental difference between Scala and Java as a programming language is that things like control flow structures in Scala are expression-based, which allows you to do things like this, which seems like a very trivial thing. But it means that Scala libraries and most Scala code can default to things being immutable rather than mutable, which I think fundamentally changes how you program in a language. Of course, there's some other syntactic differences. For instance, I could write it this way in Scala, but that doesn't really matter. Maybe you really like curly braces and parentheses and things, but you don't necessarily need them so much in Scala. So the kind of takeaway, and it's quite a simple one really, is that if you're statement-based, you typically have to have side effects, where if you're expression-based, then your programs can evaluate to values. And the purest form of this is your pure functional programming in things like Haskell and parts of the Scala ecosystem, where your entire program evaluates to a value and has no side effects. And you probably think, why would you want to do that? And I'm not advocating that. I'm just saying that if we make a large part of our program evaluate to values and work with immutability, then I think we get an easier program to read about. So the other part of functional programming, which I want to take into Scala, is referential transparency. So again, if all of your program just evaluates to a value, then it's referentially transparent. And what does that mean? So imagine we've got a value that's x, and the question marks is actually valid Scala syntax. It type checks to anything. It type checks to the bottom of the type system. And if we have a value y, which is derived from the value x, and it's x times x, what does it mean for this statement to be referentially transparent? Or more accurately, what does it mean for this expression to be referentially transparent? Well, it means that if I were to be able to substitute x, the right-hand side of x, so these question marks, whatever code I were to write there, into the expression that creates y, then I'd end up with the same program. So hopefully it's quite clear to see that if the value of x was 4, then this would be a referentially transparent program. And there are many benefits to this. You can substitute things, you can reason about them, you don't have to look at the implementations of functions if you know they're referentially transparent. But what about this? Is this referentially transparent? Well, I would hope the answer is no, because if we were to substitute this value of x into the above expression, then we'd end up with the thing printed twice rather than once. And this seems like quite a trivial thing, but this could be hitting a database, this could be adding latency, this could have the side effect that if the database was down for the second time, then the function that your program would blow up rather than work. So I'm going to use the terms referentially transparent, semantic syntax, and all these things quite a lot, but now let's jump directly into one of the main topics of the talk, which is function composition. So, what is functional programming? Well, functional programming, there's many definitions, but in reality it kind of just means composing your software out of functions. And one of the fundamental techniques for doing that is function composition. And function composition allows us to take different functions and stick them together to create our actual business software. And there's some wonderful benefits to this, is we can completely independently test our functions, and apart from the types that need to line up between them, we don't need to worry that they're not coupled like they would be if you're passing independencies, say into an object. The example I'm going to use is a basic HTTP request. And whatever web framework you're using, or web library, and I'm assuming a lot of people here are doing HTTP things, I'm going to guess that the fundamental part of it is taking HTTP requests and putting them into HTTP responses. If you haven't seen this before, this syntax or this piece of functionality in Scala is called a type alias. And the bit on the right of the type alias is just the syntax for saying it's a function from HTTP request to HTTP response. Type aliases are a really cool feature, I think, because they allow you to give names to what could be quite complex things, which makes your code more readable. So to do that, we're going to need some classes. We're going to have some data involved in this. And if you haven't seen this before, this is a case class. A case class in Scala is immutable by default. It's a value object, so it's the equivalent of if you're using Lombok or immutables in Java, or if you're using IntelliJ or Eclipse to define a hash code in equals, which is based off the value of all of the fields. Of course, this is just a syntax difference between Scala and Java. You could create the exact same thing in Java or C#. It would be a lot more verbose, but you'd end up with the same functionality. And normally I don't care too much about syntax, but this is the one bit of syntax which I think is extremely important in Scala, because it allows me to define my entire domain model, my entire set of data classes on a single page. And that's what I would typically do in a project if I was using Scala or something like F# as a programming language. Whereas if we have to put them in separate files and there's lots of boilerplate, it means I can't just look at my domain in one file. The next thing we're going to see is a trait. We're only going to use traits in Scala as interfaces in this talk. So I'm guessing if you're taking things from the internet or things from the network, at some point you're going to have to turn them into bytes, or from HTTP requests and responses into some classes that we can program to. So I'm going to guess they're just functions from customers to HTTP response and HTTP requests into people. We're quite used to this layered architecture in our ecosystem. So we often have things like controllers, or call it whatever you like. It's the thing which knows about the HTTP library you're using. And you might be using some annotation-based framework to do this, but essentially the first thing you'll typically do is somehow turn it from a HTTP request into some kind of useful thing that you can program to. We then probably pass it to some service, some other code which is down here, which doesn't know about our HTTP framework. And then finally, when we get the final result, we need to serialize it back. And this is one way of structuring our application. What does the application service look like? Well, it doesn't really matter for this talk, so I didn't actually write any application code, but we can validate it, we can decide whether we want this person as a customer. Maybe we do, maybe we don't, maybe we like them, maybe we don't. But at some point, we might want to save it, so we might interact with the database, but because we want to keep our abstraction layers very separate, we'd say, okay, that's kind of infrastructure. I don't really want my domain proper code to know about databases, so I'll inject some kind of repository or infrastructure class, and again, that would be a trait. Who here structures applications kind of this way, where you separate HTTP, database, and core business logic and call between them? That's most people in the audience. So this part of the talk is about doing it completely differently, because what I would say is that way of structuring your code is kind of like do-it-yourself wiring. So there are two things going on here in the code we've seen so far. There's dependency injection. So that's when we pass our customer repository into some service. That's the first bit of wiring that we're doing ourselves. But we'll often use some kind of DI framework for that, which is probably based on reflection. The other bit of wiring we're doing is the interaction between the layers. And it's quite common then to think, oh, because I want to make sure that my business logic does eventually make the customer persistent, I'll probably test it, perhaps with a mocking library or some similar mechanism. What I want to suggest is that we use some language features to avoid having to do this, which might reduce the amount of testing we have to do, and certainly will reduce the coupling between these layers. Because even if you pick a really good interface between these layers, you're still passing in an implementation of it. The code is still coupled together. It could obviously be worse. And the language features we're going to use are function composition, currying, and partial application. So to describe these, I'm going to move away from the web request example, go to something really simple like adding and multiplying numbers, and then apply it back to the HTTP example. So here's the most complex function I've written, or certainly in the last 5 minutes. It's add. It takes two integers and adds them together. Here's a specialized version of that function. So I've taken a bit of code which I've written, and I've created a more specialized. And this is a way to basically partially apply a function in a language which doesn't support currying and partial application. And I've done it manually. I've just said add, and I've hard-coded 10. I could have another function called multiply, which does the same, and then I could partially apply that. And hopefully you can see the bit at the bottom. The other thing we can do is we can compose functions together to create new functionality. So if you can't see the bottom there, because I realize it's a flat room, then what I've done is I've created a new function. It takes in an integer, it passes it to add 10, and then the output of that goes into multiply by 10. And just like the layered architecture, which explicitly calls from layer to layer, I'd say this is, again, doing the wiring of function composition myself. So how could I do that in Scala? Well, first let's do it the same way. So I've got an add function. I've got an add 10 function. The syntax is slightly different, but fundamentally this is the same code. The bit of functionality which you've got in Scala, which you don't have in some other language, is the fact that you can define curried functions. A curried function is one where each parameter is separate. So you can pass one parameter in, and then what you get back is a function with one fewer parameters. And in Scala, you have to be explicit about it. In certain languages, you don't. And the advantage of that is I don't need to pass in all of the parameters. So what I can do is I can take this curried function here, and I can just call add, I can call it and pass in one of the parameters. And I guess the question to think about is, what type is that? I've assigned it to a value. What type do we think that is? It's a function from integer to integer, because we've just partially applied it. Now, because Scala has this weirdity that things aren't curried by default, you can just take the top one and call .curried on it. So that would be the equivalent code. So let's just see that of the original example altogether. So we have two curried functions, add and multiply. And then if we wanted to combine these by partially applying them, by specializing them, and then sticking them together, we can do it in one line in Scala. So we can say we're going to do add 10, then we're going to compose multiply by 10. And that's the equivalent code. The only difference is we've used a built-in bit of functionality in Scala. The first is the curried function, which allows us to partially apply, and the other is the compose. So compose goes from right to left, which works well in maths, but sometimes when I'm defining business functionality this way, it works better the other way. So Scala has two functions for doing function composition. It's a mouthful. One is a compose, which goes from right to left, and one is and then, which goes from left to right. So these two pieces of functionality are the same thing. Now, these two terms, currying and partial application, they can very easily be confused because they're very intertwined. So just to make sure it's clear, currying is the piece of functionality which allows us to define functions which take multiple parameter lists. And the pure version of it is that each parameter list just takes one parameter. Partial application is making use of that currying so that we can specialize our functions and create new functions from existing ones by only passing in a subset of the parameters. And function composition is gluing two functions together. So that a simple example would be if you have a function from string to int, and int to bananas, and you want to compose these together. First, the types have to line up, so the output of f has to be the input of g, and we can write g compose f, or f and then g. Now, I'm guessing not many people work in the domain of turning strings into bananas, so let's go back to something a bit more realistic, which is this. So this was the original code. This hasn't changed from before. It's all the same code. Our goal is to build a function from HTTP request to HTTP response without doing any explicit wiring and calling things like calling between layers explicitly. Just to remind you what the application service looks like, it looks a bit like this. So the end goal is to end up with a function from HTTP request to HTTP response, because that's what we do most of the time. We just do HTTP and gRPC and backend apps like that. And if we think about deserialization, right, that really is just a function from HTTP request to some object which has been validated and you care about. So I'm going to say that we're going to turn HTTP requests into people, into persons. Now, we then need to decide whether we want to turn this person into a customer. And I would say, rather than all that trait and class stuff, that's really just a function from person to customer. Saving a customer. So we're talking about interacting with a database. That could be a function from customer to void or unit in Scala, or it could be a function from customer to customer if it's augmented somehow, say with some kind of ID. And then the final step is obviously to go back to something our web layer, our web library understands. So that would be a function from customer to HTTP response. So can anyone kind of imagine now what our program will look like rather than the traits and the layers and the classes? Well, it's just one big set of function composition. And this is perfect. This is compiling Scala code. I haven't implemented the functions. I'm not going to worry about that. But right now, the function which I can give to my web framework, now it could be class and method based, but there's nothing stopping me from constructing my code this way, is I deserialize the person, I create the customer, and then I save the customer, and then I serialize it. And this type checks to a web request. And the thing I really like about this, and I think this works really well for things like request response, it works really well for like data pipelines, I've written Spark code this way, is that each of the functions are completely independent. You can test them without mocking and passing things into each other. The only dependency between them is that the types have to line up. So I think this is like really good for building like decoupled code. So I guess the question is, are we done? Is this going to work? Are we going to be able to build our applications this way? Well, if I look back at the functions, I look at this save customer. Who here has written a function which saves something to a database without something like a database connection? That's a bit, I think I've made them too idealistic. So the next step is, how do we deal with things like database connections and HTTP client libraries and all the things we actually need to make useful code work? And that's where currying and partial application is going to work, because function composition in reality is not going to work for us in real life applications unless we can massage our functions to make the types line up. So my assumption throughout the rest of the talk, I don't know what database library people use, but there's going to be some object which is the database connection. And if I'm realistically going to write a function which saves something to a database, I'm going to assume that function requires one of these. So we'll talk about different ways to get that in there. So if you haven't seen Scala objects, they're just a way of defining functions. Everything is static. You can't instantiate them. It's a way of grouping like-minded functions. So my save customer function is now going to be a curried function, and its first parameter list is going to be a database connection. Its second one is going to be a customer, and it's going to return the saved customer. So if we want this to work with our lovely idealistic web request, which goes from HTTP request to HTTP response, all we need to do is partially apply this function. So in the bootstrap portion of our application, inside your main method or however your web framework starts an application, what we do is we create our connection pools, these kind of things. We can partially apply the functions, and then we can compose our requests and our logic. And this definitely isn't pure functional programming. Someone would hit me with a stick if I even suggested it would. It's definitely not referentially transparent now, but we're still using language techniques rather than explicitly passing things between each other. And because this type checks to customer, we can then use this code again. So that's one way of doing it. But who here writes one function which interacts with the database? Normally you've got lots, right? You're saving lots of things, you're retrieving things, you're updating things. So that's where classes in Scala become very useful. So one way of thinking about a class, and if you've not seen the syntax, it's the same as having a constructor in Java, having a set of private final fields. It's just slightly less syntax to consume. But another way of thinking about a class in Scala is a group of curried functions, where the first parameter list is the constructor, and the second parameter list is whatever happens to be on the function, on the methods. It just happens that we've got 6 methods that interact with the database. All of them need a database connection, and I don't want to type database connection parameter list in front of them all. So when I instantiate this class, I can think about this of partially applying all of these group of functions. Now, I've only got one, but imagine you had many. And then, when I need to compose my application, I can pull off a method from a class, from an object, and I can still type check it from customer to customer, except it's going to be using that shared database connection. I find this, again, a useful way to structure applications. Another way of doing it, and the final part of this talk is going to be talking about implicits, but another feature which Scala has here is the ability for the final parameter list to be implicit. And what that means in Scala is that the compiler itself will look in the current scope for something which type checks to that parameter list, in this case a database connection, and it will pass it in for you. If there's more than one in scope, it will be a compiler. It'll be like, which one should I pass in? And this is definitely a controversial way to do things. Some people like it, some people don't. Often the gateway to Scala is doing Spark, and Spark uses this a lot. You don't explicitly pass around the Spark context, the equivalent of your database connection in a Spark application when using Scala, but you do when you're using it from Java. Inside Akka, we use this very sparingly, just inside passing around things to allow us to materialize the streams and things. But for this to compile, if we still want to get back to a function from customer to customer, when we write this, when we assign it to a variable of type customer to customer, the only way this will compile if this is in scope. So there's a database connection, and the only difference for when we've defined it before is it has the word implicit before. So implicits in Scala are quite explicit. It doesn't instantiate things. It's not like a DI framework, which is going to look at the class, have a look, and instantiate it for you using reflection. This would have to be valid at compile time. So that is the end of the section on this topic, but not the end of the example. We're going to keep expanding that example as we go through the rest of the talk. So the techniques which we've gone through are function composition, currying, and partial application. And come to think of it, I don't actually think these are the main benefits. I think the main benefit is the fact that the functions are completely separate and testable, and the fact that they're decoupled. So the next thing is higher-kinded types. This is a feature which may become mainstream in programming languages in the next 5 years or so. I hope. So, types. We all like types. We're all at a DevOps conference. I assume there's some JavaScript enclosure and things here. But we like static types. I like static types. We've got different types of types, right? We've got types like string and int and person and customer. These are real, proper, concrete types that we can like hold and lick or something. And then we've got these other type of types in Java and C# and Scala. The difference between them is these aren't really proper types. They take something, a t, like a string or an int, and then they become a proper type. They're often called generics or parametric polymorphism. And another way of thinking of these is that they're a function that takes in a type and gives you a real type, like list of string rather than list of t, something you don't know. Of course, in Java, for backward compatibility reasons, list is a real type, but you get compiler warnings if you use it that way as of Java 1.5. We can write these types of types with more than one parameter. So map, for instance, takes 2 of them before it becomes a real type. And this is obviously not a feature which is unique to Scala. This is obviously in Java and C# and other languages. The feature which is unique to Scala and other more powerful programming languages, so not unique, is being able to abstract over them. So we're used to creating abstract code that's based on generics. We like putting T's and angle brackets and square brackets if you're in Scala. That's a very common thing. But when you moved from Java 1.4 to Java 1.5, I bet you, or I certainly had a little problem with all that new syntax that was there. Because we're very used to now this. I'd say most developers see that and don't even bat an eyelid. But imagine if you could abstract over the other side. A name for things like list and set and future and all these things which take a type parameter, in most literature it's called a type constructor because it constructs a proper type. Now, this is weird to me. T isn't a real type here, by the way. It's representing something like a type variable. So we're going to write a function which takes anything that takes one type parameter that's an integer. That's a little bit weird, isn't it? Whereas we could actually abstract over both, and that's by far, that's very common. And I find that very weird when I first came across this feature. You end up with very abstract code. So before we dive into what the syntax is like in Scala, I want to talk about a motivation for learning about this feature. So the world is going asynchronous, I think we'd agree, especially as we're building services which tend to call out to other services because someone told you to do microservices. But they definitely probably talk to queuing systems and databases. And one of the scalability bottlenecks that a lot of applications have is the fact that it's a thread per request. A thread in Java and the JVM is an operating system thread, which is an expensive resource. So web servers these days, so Akka HTTP represents a web request like this, and you've got reactive spring, and this is very common these days. A future here, do not think of the Java 1.5 future, think of the Java 8 completable future, and they're very, very similar in Scala and Java. So instead of representing our HTTP request as one that goes from HTTP request to response, we're going to stick a future in there. The goal of this is so that when we interact with databases and queuing systems and calling out to other services, is we're not going to block an operating system thread so it can be used for other requests. Another motivating thing might be that we might want to stop using exceptions. Some people like exceptions, some people don't, some people think they'll go to. I'll let you decide. And one way of doing that in Scala is to use this thing called an either. And this is where you basically say, I'm going to return a HTTP response or some type-checked error, like a throwable, but you don't throw it, you just pass it around, or just some custom enum that you're passing around to say what the problem is. Now, before we see how higher-kinded types and abstracting over them can help us, we have to address the fact that we've completely broken our function composition. All that stuff I've just talked about in the previous section is broken because we've introduced parts of our logic, like interacting with databases and queuing systems and calling out to services. They will need to return futures now, or something equivalent, like a RxJava observable or a completable future. And I'm going to assume serialization is still going to be synchronous and CPU bound. So serializing something and deserializing something, I'm going to assume those function signatures are going to remain the same. However, creating a customer, maybe that involves a call out to some external registry in your company to see whether they're already a customer or whether they've been blacklisted. So I'm going to make that one a future, and I'm going to make saving a customer a future, because that definitely will be asynchronous. And if we go back to our function composition, we get about this far. We can deserialize the person, and then we can create the customer, but then we end up with the wrong type. Rather than HTTP request to customer, which would compose nicely with our saved customer, we've got a bloody future in there, which is very upsetting. And we're going to use two functions to fix this. I think we only need two. One is called flatMap. This is a function on the Scala future. It's called then compose on the Java completable future, and map on the future, which is called then apply on the Java completable future. What does this allow us to do? Well, it allows you to take a future of something, A. In this case, what do we have? I've forgotten. We have a future of customer. And then it takes another function, which goes from that A into another future, because it's another asynchronous computation, and it returns a future of B. And that's going to allow us to put in our save customer, because that's the type signature it is. It happens A and B are actually the same type in this case, but that doesn't matter. So let's see how that works. So we'll just define a function on the fly. So this is a way I can just create a function on the fly. So I'm going to take in a HTTP request, which is the HR on the right-hand side there. I'm going to call the first step, the function composition that still worked, and then I'm going to call flatMap with save customer. And that gets me nearly there. The last thing I need to do is do the serialization. Now, that didn't introduce any new features, so we're not going to implement that with flat map, we're going to implement that with map. And we can actually do all this on one line with a for comprehension, but I won't go into that because that's a whole new set of syntax to introduce. And this pattern is very, very common. As soon as you start representing things like asynchronicity in the type system with something like a future, you always want to be, you don't want function composition to go from A to B and B to C. You always want this extra thing in here, like a future or a completable future or something else. And I called it supercompose, but it's got fancy names in some libraries. If this is interesting to you, there's a whole book which will teach you about this in Scala, or just this very particular concept. There's a blog there, and I'll tweet out my slides if you want to read about this. But rather than use that cool library, which is called cats, which is an excellent name for a software project, we're just going to write all of the same code again, but we're going to use either, because we changed our mind between wanting to use futures or eithers. Well, not really. So, lots of new syntax on this slide. What we've got here is a type parameter, which we're used to having, but normally it's like A or B or T, but it's got a weird thing after it. It's got like an underscore. What this means in the Scala programming language is it's some type, we don't know what it is, but the only thing we know about it is it takes one type parameter. And this is what we mean by abstracting over these type constructors or higher kind of types. We can actually write things like classes and things, and we can have a type parameter which is just some type constructor. That type constructor could be list or future or completable future. It could be anything. However, if it was anything, it'd be pretty damn useless, because what can you call on anything? Hash code? Equals? Not very useful. So the other bit of syntax that we're going to introduce, the other feature, is to say, okay, I need to be able to turn it into a mappable. And what's a mappable? Well, a mappable just has two functions, because they're the only functions we used. Our business logic obviously deals with customers and all of the other things there, but when we were doing our composition, we only used two functions. And wow, that's a lot of square brackets and stuff, but we don't need to worry about that. You just need to take away that the functionality this is going to give us is we can write all of that composition in terms of some type parameter, which we're used to doing. The thing we're not used to doing is that type parameter is actually something like a list or a future, and we can decide later. And if I'm not going to show all of the machinery that's required for that, but if you want to see it, it's in the example project. But let's see how the composition works now. Well, we're not dealing with futures now, we're dealing with something. We don't know what it is, it's just f. And we can still compose our two functions from this. We can still deserialize and we can still create the customer. And we can then use flat map, because we know, the only thing we know about f is it's got flat map and it's got map. So we can still do the composition we directly did with future, but we don't know what it is yet. And we could instantiate a version of this for future, and if I were to type check this full request, it wouldn't be from f, because we've specialized it down to a future. That's a weird feature, and that's something that there's not really an equivalent thing that you can say, oh, it's a bit like this in other programming languages, apart from languages like Haskell. And the question I would be thinking about if I was in the audience was, is this useful? How often do you want to do this? Well, about 5 years ago, the last time I worked on a big project in a language which didn't support higher kind of types, it was Java. It needed to be asynchronous for scalability. So we needed some async web framework, and this was Ratpack. I'm not sure if you've ever used that. Ratpack has its own asynchronous construct, like it's called a promise. We used Hystrix because Netflix told us to. And Hystrix is a library for wrapping external requests and putting things like circuit breakers and deterministic timeouts and logging. They, if you want to be asynchronous, use RxJava Observable. We had a database, because everyone has a database, and that was using Guava listenable future. And then our own code, and code within the company, was using Java 8's completable future. What do you think our code looked like? It was just converting between these types. The business logic was lost in it. All of these types here, they take one type parameter, so we can abstract over it, and they all have a function which does exactly what flat map does and exactly what map does. So the last section of the talk is implicits, because I very foolishly maybe, or very quickly said, oh, you can just call flat map on it because of that type, that f was there with its mappable. But implicits, which are quite a controversial feature, they're required to build the machinery so the previous code worked. And the takeaways kind of from the implicit section is I think most sensible uses of implicits in the Scala programming language replace runtime reflection. So things like serialization libraries and dependency injection, all these things We're either going to use implicits or we're going to use partial application, etc. And for me, the big advantage of implicits in Scala is that it's a language feature which I get to learn, and then it's applicable for the rest of my career using the Scala programming language. If I learn how a particular framework uses reflection to achieve something similar, it's completely proprietary to that framework, and it's not like a transferable skill. Fortunately, Spring is so dominant that it probably will be applicable for the rest of your career. And I think it goes without saying that the implicit features I'm about to show you are far more explicit than reflection, because A, they're at compile time, and B, there's rules associated with what they do. However, because I'm a realist, I'm going to talk about a terrible use of implicits and one which really kind of gives them a bad name, and that's type conversions. So in Scala, you can explicitly convert from one type to another using an implicit. And a terrible use case, in my opinion, of course this is subjective, is to go from a concrete type like cat and turn it into a concrete type like dog. So imagine, I've had dogs before, and they get very dirty when you take them for a walk. So what I'd really like to do is be able to clean the dogs. All case classes in Scala have a copy constructor where you can just override certain fields. That's what that is. And I can just say the status of this dog is it's been cleaned with a hose pipe. Right, I have a cat, I have many cats, one of which my cats is called Ruby. Now, do you think, in a statically typed programming language, that we should be able to pass Ruby into clean dog? Who thinks we should be able to clean Ruby with a hose pipe? No one? One person thinks it. Right, this is Ruby. Who still thinks we should be able to clean Ruby with a hose pipe? Anyone? There's two now. What? Oh, she helped me prepare the talk. Anyway, Ruby's quite a nice cat. If I cleaned her with a hose pipe, she would forgive me within a very short amount of time, and she'd be back on my knee. Her sister would not forgive me. She's a very picky cat, and when I suggested to her that she was cleaned like a dog, that was the facial expression that I got. However, you can do this in Scala. In a statically typed programming language, I could write this, which I think is a very bad use of implicits. Of course, I've said a couple of times that implicits in Scala, you need to explicitly use them. You need to bring them into scope. So I would have to have a function like this for this to work. And for those at the back there, it's a function which turns cats into dogs. Why you'd want to do that, I don't know. And the only difference is it's got the word implicit in front of it. And that means the Scala compiler, when it's time to type check this thing here, this clean dog with the Ruby in, if it doesn't compile, it can search around all of the implicits in scope and turn poor Ruby into a dog and then clean her. I think the only really good use case of this is when building embedded DSLs in certain libraries. But at that point, you're not really programming Scala, you're programming to the embedded DSL, and those kind of things you just have to learn. But I'm not a fan. One thing I am a fan of, though, is something I'm going to call principal type conversion. Don't know why it's principled, really, but it's going to be principled. And we've already seen this. So if we create types like this mappable, and the only way we can turn things like futures and completable futures and ethers into this type and use it as a mappable thing is via an implicit conversion, I think it's a good thing. One of the reasons why I think it's a good thing is if I want to find out what implicit stuff is happening, what do I need to do? The only thing I need to do is find the implementations of this trait, which means that I can just go into my IDE, press Control-Shift-B, and it tells me all the implementations, and I know which types in my ecosystem can conform to this mappable, so I know that my business logic can be defined in terms of them. What does that machinery look like? Well, what we need for the previous code to compile that I showed you with the colon mappable after the F is this in scope. So we need to show the Scala compiler how a feature is mappable. And it's really quite straightforward to make a feature mappable because we pick the methods on mappable from methods on the Scala feature. So we just call map and we just call flat map. It's not always as easy. So if we decide that we don't like Scala's feature and we, for some bizarre reason, wanted to use the Java's completable feature from Scala, then we could do the same thing. So it's been cut off a bit, but the important thing to note here is I'm still making a completable feature mappable, but I'm calling different methods. On the completable feature, I'm calling then apply, or I'm calling then compose. And I think this is a really good use case of implicits inside Scala, and it allows a lot of the cool functionality that you probably rely on if you program in Scala. So I had a bunch more uses of implicits, but I had to cut them off because I was going to run out of time. so the kind of summary of the talk is that what I really want to show was that we can use like features of a programming language. It doesn't need to be Scala, it could be whatever, rather than relying on things like runtime reflection. And some of the most important one, I think, is the function composition over layers. I really like structuring applications that way. The higher kind of types thing is going to be very hard to use something like that unless you move to a programming language like Scala or Haskell. And I wanted to like give a sales pitch for Scala implicits, because I actually think they have a bad name, and there's some really good use cases of them that offer some good functionality. That said, if I've somehow, unsuspectedly, inspired you to go and find a new job in Scala, or convince your team that you should use Scala, these are kind of my top tips that maybe I didn't follow when I first moved, is you really need to be prepared to be a beginner in this programming language. It's not like moving from Java to C#, which maybe the syntax and the runtime changes a lot, but the semantics of it are very, very similar. Or moving from, say, even Java and Kotlin are far more similar programming languages. Scala really is a different paradigm. The collections you use work in a completely different way. By default, you'll be using persistent immutable collections, which are completely different and have completely different behavior and runtime costs than the ones you'd say be used to be using in something like Java. And you really do need to pick a programming paradigm in Scala, because you could write it just like Java. You could use mutable states, and you could not program in terms of expressions and values. You can do that. And you can program as if it was Haskell. Like, there's that broader spectrum of ways you can use the Scala programming language. I really hope that you would pick something in the middle, use some of the cool features which you don't have in other programming languages, but still reuse a lot of the useful knowledge that you've gained by doing object-oriented programming. And of course, pick a style guideline. And one thing the Scala ecosystem has is a lot of static analysis tools. And there are some gotchas in the Scala programming language, but there's things like wart remover, like a build pool plugin that'll say, do you really want to do this? You're falling into one of the traps of the programming language. And on that note, I just want to say thank you very much for listening. And we've got a few minutes left for questions. So, has anyone got any questions? Yeah, one there. There we go. Any more questions? So the project there is basically an SBT project, which is the build tool for Scala, and it builds a set of HTML slides as well as by pulling the code out there. So you can go around and play with the code. It's also got the full mechanics required to make the higher kind of type stuff work. And it's not using like a library or anything. It's got all the code is there. But in reality, if you're doing that style of programming, you'd use a library called like Cats, which is an awesome name. Any more questions? No? Brilliant. Thanks very much for listening. Thanks for coming.